Hey guys, so let's discuss the conical pendulum. We discussed the scenario in which the mass attached to a string was rotating in a vertical circle, right? Now, if we rotate the same object in a manner such that the mass sweeps a circle and the whole string and the mass system sweep a cone, then we get what is called a conical pendulum. Okay, so so let's say this is the mass, right? And it's moving in a horizontal circle. Okay, the forces acting on the mass are just tension along the string and weight, which is straight down. Okay, now you can let's call this angle theta. Okay, so if this angle is theta, this is also theta. Okay, simple situation, this is theta, then this is theta. Okay, now since this again object is moving in a circle, there's a force that's towards the center that's keeping it in a circle. We have to figure out which force or which component of these forces points towards the center. So you guys should have some idea. Pause the video and think about it. Which component points towards the center, or which force should we resolve? So let's take a look at the side view. So here's tension, here's weight. Okay, now you can see that weight is already vertical. There is a component of tension that's towards the center, this component. Okay, and look, since this angle is theta, we want to write the component in terms of this angle. So this component that's towards the center, okay, of the circle is t sine theta. Okay, so this is the center. Now this is t sine theta, so this will be t cosine theta. Okay, so this is t cosine theta. So Newton's second law, again, let's try Newton's second law again. Net force in the radial direction is mass times acceleration, which is the centripetal force in this case. So t sine theta is equal to mv squared over r. Now r is the radius of this path, of this horizontal circle. Okay. Now let's call this equation 1. The net force in the y direction, there's no motion in the y direction when you rotate the object in this way. There's no vertical motion. Okay, so you get the net force in the y direction equal 0. So you get t cosine theta minus w is equal to 0. So t is w over cosine theta. So that's equation 2. Now let's plug 2 in 1. So plug 2 in 1. So we get, so 1 is w over cosine theta times sine theta equals mv squared over r. So you get w is mg. I'm going to write mg over here. Okay, the mass cancels out. Again, independent of the mass, you get v squared equals rg tangent theta. So v is equal to square root of rg tan theta. Now looking at this, let's look at, so you can see that this is a right triangle, right? This is right triangle where L, the length of the pendulum, is the hypotenuse, and this is the radius of this side is the radius of the horizontal circle. So let's write over here. So you get L, and then this is theta, this is r. So you can see that r is L. I'm just showing you the side view, the way this triangle is shown. This is a right triangle actually. Okay, so the r is L sine theta. So let's, you can see that r is L sine theta. Now, if the object can be rotated in a way that the velocity or the magnitude of velocity remains constant. So in that case, we can define a time period. If the magnitude of velocity is constant, we can define a time period. So let's call that t prime. T prime is going to be 2 pi r divided by v. So this is the time period, is time for one complete oscillation. So it's the distance in one complete oscillation is 2 pi r, which is the circumference of the circle. V is the speed. So let's let's plug in v. So if you plug in v equals square root rg tan theta, you get 2 pi square root of r over g tan theta. Now let's plug in r equals L sine theta. So when you do that, you get 2 pi square root of L sine theta over g tan theta. So your expression for the time period is 2 pi square root of L over g cosine theta. So that's your equation for the time period of the conical pendulum. 2 pi square root L over g cosine theta. So this was the conical pendulum. If you have any questions, post them in the comments. Thank you for watching.